Hi, my name is Andrew, and I'm a PhD student at the University of Chicago. In my lab, we study semiconductor materials. Semiconductors are used to build the processors and displays in your smartphone and laptop. Today, I'll be talking about something different. Today's topic will be the science and engineering behind sound and music. Other than being a researcher, I'm also a musician. I grew up playing the trombone, and recently I've also picked up playing the trumpet. To start off with, we first need to answer one simple question. What is sound? Well, sound is all around us. We hear it with our ears. It could be a car driving by, it could be a bird chirping, it can be music coming out of a speaker. But what is it? Well, it's hard to visualize sound because we don't see it with our eyes. But if we could see it, what would it look like? So if I clapped, what would that look like? If we could see all the little air molecules around my hand when I clap, we would see that there's actually a wave that happens because of the motion of my hand. And that wave travels outwards from my hands to my ears. So that's what a sound looks like. But how is a musical note different from just a regular sound? Well, to start off with, musical note isn't just usually that short, right? There's some length to it. You hold it out for a little longer. And so if I were to pick up my trombone and play a note, it wouldn't look like a single wave of sounds like with a clap. It would just keep going until I stopped playing my instrument. But there's another quality to a note that's a little different too. There's something musical about it, right? If I kept clapping, of course I would make a bunch of little waves, but it wouldn't sound like a musical instrument. Why is that? Well, to answer that, we also need to discuss what is a wave. A good way to visualize what a wave is by playing around with a toy in which we fix 2 points with a string in between. In this model, how can we move the string and vibrate it? Well, we can wiggle it around the center like this, and it'll still be fixed at the 2 endpoints. Frequency is a scientific word for what musicians call pitch. A high-pitched sound sounds very high, and a low-pitched sound sounds very low. We can change the pitch by moving the 2 fixed endpoints. If we move them closer to each other, these wiggles get even smaller. And the smaller the wiggle is, the higher frequency sound something is. The longer a wiggle is, the lower frequency sound something is. One way to visualize this is with a trombone. A trombone has a slide in which, by sliding it out, the instrument gets longer and longer, right? And so if I were to play a note and then I move my slide out, that would make the note sound lower. That is the same idea as moving the fixed endpoints on a string. But we can actually wiggle it so it goes up and then back down, so that in the middle there is a point where it doesn't move. So now we have 2 wiggles. And we can keep doing that. We can have 3 wiggles, 4 wiggles, and so on and so forth. The more wiggles that we have, the higher frequency a sound sounds like. The first example with a single wiggle would be a low sounding note. The second example, with 2 wiggles, would be a higher sounding note. The number of wiggles that fits in a string is called the harmonic. Well, the tone of a musical instrument is actually adding all these wiggles together, all these different harmonics. And different instruments have harmonics of different strengths. For example, one instrument might have a very small first harmonic, a very large second harmonic, and the third and fourth and so on are very weak. While a different instrument might have a very large first harmonic, a very small second harmonic, or a large third harmonic. So this is what determines an instrument's unique tone. Sometimes musicians call that the instrument's timbre. So if I played the same note on a trombone, or on a trumpet, or on a violin, or on a guitar, if we were able to look at each of these harmonics that comes out, it would sound different even though we're playing the same note. So the demo here today is called a harmonic spectrum analyzer. This allows us to look at the harmonics of an instrument. So if I play my trombone up and down, you can see how the harmonic spectrum analyzer reacts to the different sounds. As we pitch down, everything goes back down, and then as we pitch back up, everything goes back up. You can see, even as I'm just playing one note, it's saying that there are a lot of harmonics coming up. Now this is what distinguishes a musical note from just a regular sound. See, if I clap, that's what it looks like. If I play a note, you can see all the different harmonics. If I sing, la, you can see also my voice, my throat, my lungs, my mouth, all work in conjunction to produce a lot of different harmonics. And each person's voice, each person's singing voice, sounds different because we all have different shaped windpipes and mouths. And that makes our harmonics sound different, and that's why some people have nice singing voices and why maybe sometimes I wouldn't consider my voice to be the best. I also have a melodica, which is basically a piano that you blow into to make sound. If I played the note F on here and compared it to my trombone, this is what they would look like. You can see their harmonics are quite different. You can install this harmonic spectrum analyzer on your own computer and try for yourself. You can even try other things like filling a bottle with water and trying to blow over it. You can also do everyday sounds like claps and snaps to see what they sound like under a harmonic spectrum analyzer. Now, the spectrum analyzer isn't just something that you can use to study sounds. In fact, a lot of things have waves, and you can also study them using a harmonic analyzer. Other things that have waves, of course, the ocean. If you've been following physics discoveries in the last few years, gravity also travels as a wave. Light is also a form of a wave. And earthquakes, as they travel through the ground, through the tectonic plates, actually move as waves too. Waves are all around us, just as sound is all around us. And so as a scientist, it has been really important for me to understand waves. But also as a musician, waves are just as important. Because that's what music is, waves. I hope you learned something today, and thanks for watching.